I have a dream that one day
Example 7 deals with application problems for GPs. And in part 1 it says a, b and the square root of 3 are 3 consecutive terms of a GP, with a being less than b, which is less than the square root of 3. If a, b and the square root of 3 are also the lengths of the sides of a right angled triangle, prove that a equals the square root of 3 into the square root of 5 minus 1 all over 2. So let's look at the solution to this question. We are given 2 bits of information and we want to convert them into equations. The first bit of information says that AB and the square root of 3 are 3 consecutive terms of a GP. So our GP is going to be A, B, and the square root of 3. We need to convert this information into an equation, and we're going to use the fundamental property of GPs. So we have term 1, term 2, and term 3. And we know that term 3 divided by term 2 is equal to term 2 divided by term 1. So we can substitute in. We have term 3 divided by term 2, and this must equal term 2 divided by term 1. We can simplify this equation and cross multiply. So we have the square root of 3 times a, which equals b times b, in other words b squared. I'm going to call this equation 1. Then the second bit of information says a, b and the square root of 3 are also the lengths of the sides of a right angled triangle. So we can draw the triangle. Now a is less than b, which is less than the square root of 3. So from that we know that the square root of 3 must be the hypotenuse, because that's the longest side of the triangle, and we can make these sides a and b respectively. We want to set up a second equation. So using Pythagoras, we know that a squared plus b squared equals the square root of 3 squared. And the right hand side here, of course, is 3. Now we're going to make b squared the subject here, and we can call this equation 2. Now if you look at what we need to prove, we see that there's no b in this equation. In other words, we need to eliminate b, and we can do this by substituting equation 2 into equation 1. So substitute equation 2 into equation 1. So we have the square root of 3 times a equals b squared, but b squared is 3 minus a squared. So 3 minus a squared. We can bring everything to the left hand side in this equation. And we basically end up with a quadratic equation in a. So we can use a quadratic formula to solve a with. So a will equal, so using the quadratic formula, negative square root 3 plus or minus, but in this case we're going to use plus only because a is a length and it can't be negative. So plus the square root of 3 squared minus 4 times 1 times negative 3. And this is all over 2 times 1. This is using the quadratic formula. So it's negative the square root of 3 plus, and we can simplify underneath the square root. The square root of 3 squared is 3, and negative 4 times negative 3 is 12. And this is all over 2. Of course, here we get the square root of 15. Now, just to look back at what we need to prove, that a is the square root of 3 into the square root of 5 minus 1 all over 2. So we can use the laws of surds and write the square root of 15 as the square root of 5 times the square root of 3. Now we can take out the square root of 3 as a common factor, and we're basically left with the square root of 5 minus 1 all over 2. And this is exactly what we needed to prove. In the second question of this example, it says, a number of circles touch each other as follows, and we are given the sketch. The area of the smallest circle is 4 pi centimeters squared, and each consecutive circle has an area 9/4 that of the previous one. If the distance AB is 665 over 8, how many circles are there? So we're going to start by writing down the areas of the first 3 circles. So A1, the area of the smallest circle, is 4 pi. This is given in the question. The area of the smallest circle is 4 pi. Then A2, the area of the next circle, will be 4 pi times 9 over 4. So times 9 over 4. And here the 4's cancel. So we're left with A2 being equal to 9 pi. Then A3, the area of the third circle, is the area of the second circle, 9 pi times 9 over 4. And this is 81 pi over 4. So we have the areas of the first 3 circles. Now, we are interested in the diameters because we are told that the length AB comes to 665 over 8. So the diameters of all these circles must add up to 665 over 8. So we're going to say let the diameters be x1, x2, x3, etc. And we're also going to use the formula for the area of a circle. The area of a circle, of course, is pi r squared, but we want to work with the diameters. So it's pi times the diameter over 2 all squared. Remember that the diameter is half the radius. So we're going to use this equation. So let's rewrite the areas A1, A2, A3, etc. in terms of the diameters x1, x2, and x3, etc. So we have A1 is 4 pi. Using this formula here, we now know that pi multiplied by x1, the diameter of the first circle, over 2 all squared must equal 4 pi. The pi's can cancel on both sides. And then we have x1 squared over 4 equals 4. And solving this equation, we can multiply through by 4. So x1 squared is 16, and x1 is the square root of 16, which is 4. Then the area of the second circle is 9 pi. So then once again using this equation, pi into x2 divided by 2 all squared must be 9 pi. Once again the pi's cancel on both sides. So we have x2 squared over 4 must equal 9. And 4 times 9 is 16. Then taking the square root, or rather 4 times 9 is 36. Then taking the square root, we get x2 equals 6. Then the third circle, A3, using this formula, we can say that pi into x3 over 2. So x3 over 2 in other words, the diameter of the third circle divided by 2, all squared. This must come to 81 pi over 4. Once again, the pi's can cancel on both sides. So we have x3 squared over 4 must equal 81 over 4. We can multiply through by 4, so we get x3 squared equals 81, and hence x3 equals 9. Now we have a sequence for the diameters of the circle. So the diameters then form a sequence 4, 6, 9, etc. And this is a geometric progression. So in this progression, A, the first term, is 4, and R, the common ratio, will be 6 over 4, term 2 divided by term 1, which is 3 over 2. Now, we know that all the diameters must come to 665 over 8. So we can turn this into a series, in fact. So all these diameters, when we add them, they must come to 665 over 8. So 665 over 8. And now we merely use the sum formula. We know that S sub n is A into R to the n minus 1 all over R minus 1. And we can substitute in these values. So A is 4, R is 3 over 2, so 3 over 2 to the n, minus 1, all over 3 over 2 minus 1, must come to 665 over 8. So let's solve this equation. In a denominator we have 3 over 2 minus 1, which is 1.5 minus 1, which of course is a half, and then 4 divided by a half is 8. Now we can divide the 8 into the right-hand side. And we get 665 divided by 64. We can take the negative 1 to the right-hand side. And we need to solve for n in this exponential equation. So we can take the log on both sides. Then, using the log rules, the n can go in front of the log. And we can divide the log of 3 over 2 into the right-hand side. And now we can use a calculator . So we have the log of the left-hand side, or rather the log of 1 plus 665. 665 divided by 64, divided by the log. So the log of 3 over 2. And our answer comes to 6. So n equals 6. In this case, n is the number of diameters and hence also the number of circles. So let's look at your answers to this question. In the first one it says, a rubber ball dropped from a height of 15 meters loses 20% of its previous height at each rebound. Determine the height that the ball will rise to after its second rebound. So let's look at the solution. We can start by drawing a sketch. So we have a height of 15 meters. So we have the floor here. So the floor. And this height is 15 meters. And the ball is dropped from this height. And it rebounds etc. Now, what's important to note here is that it says each time it rebounds, it loses 20% of its previous height. So it only bounces back 80% each time of the previous height. So on the first rebound, it will attain a height of 80% of 15 meters. Then on the second rebound, it will attain a height of 80% of the previous height that it reached. And we can construct a GP of its rebounds. So rebounds. So this will be of the heights that are attained each time it rebounds. Now we're going to exclude the first height of 15 meters. On the first rebound, it's going to be 80% of 15 meters. So 15 times 0.8. Then on the second rebound, it's going to be 80% of this value. In other words, the height it attained on the first rebound. So 80% of 15 times 0.8, which is 15 times 0.8 squared. And then on the third rebound, it's going to attain 80% of this value. So 15 times 0.8 cubed, etc. Now, the question says, find the height that the ball will rise to after its second rebound. In other words, on its third rebound, which is this value here. So we have the answer to 1.1. So the height on the third rebound will be 15 times 0.8 cubed. So we can do this on a calculator. So 15 times 0.8 to the power of 3, and it's 7,68 meters. So 7,68 meters. Then in 1.2 it says, determine the number of times it will rise to a height of over 3 meters. So let's go back to this GP we have over here. We're going to work out the exact values. So 15 times 0.8 is 12 meters. Then 15 times 0.8 squared is 9.6. And here we saw that 15 times 0.8 cubed is 7.68. So these are all the heights on the rebounds. So what's important to note is that the height is getting smaller and smaller and smaller. At some point we're going to get a rebound or a height that's less than 3 meters. Now the question says, determine the number of times it will rise to a height of more than 3 meters. So we know that this is a GP where A is equal to 12, the first term. The common ratio R is 0.8. In this question, in the second part, the number of times it will rise to a height of over 3 meters. This tells us that we must find the number of terms here that is greater than 3. So we are looking for n, where t sub n, the nth term, is greater than 3. So we're going to use the formula t sub n is ar to the n minus 1. And then plugging in our values, we see that A is 12, R is 0.8. So A is 12, R is 0.8. We're looking for n, and this is t sub n. So this must be greater than 3. So we're looking for n. We're going to first divide by 12 on the right-hand side. So 0.8 to the n minus 1 is greater than 3 over 12, which is a quarter, or 0.25. We could use exponents here and convert these decimals to fractions, but let's stick to logs. So we log both sides. Now we can use the log rules and write n minus 1 in front of the log. So n minus 1 times the log of 0.8 is greater than log, or the log of 0.25. Over here, of course, we're using this log rule that says the log of a to the m is m times the log of a. We can now divide the log of 0.8 into the right-hand side. But now what's important to note is that 0.8 is between 0 and 1. So the log of 0.8 will be a negative number. And when we divide by a negative number in an inequality, the inequality switches around. So it's going to be from greater than to less than. So it switches around when we divide by log of 0.8, or the log of 0.8. Now we can do this on a calculator. So it's a log of 0.25 divided by the log of 0.8. And we see that it comes to 6,21. to 2 decimal places. So 6,21. And then solving for n will be less than 7,21. Now, n is the number of terms. It must be a natural number. And the natural number just below 7,21, of course, is 7. So n is equal to 7. So that means that there are 7 terms in this sequence that will be greater than 3. So the number of rebounds that will reach a height of over 3 meters is 7. So in number 2 it says, from a length of string, pieces are cut so that the lengths form a GP in descending order of length. The third piece is 10 centimeters and the length of the sixth piece is 1,25 centimeters. And in 1 or 2.1, we have to find the length of the first piece. We're going to start by writing down the GP. We don't have the first length or the length of the first piece of string. Neither do we have the length of the second piece of string. But the third piece is 10 centimeters. We also don't have the lengths of the fourth and fifth pieces. But we are given the length of the sixth piece. It's 1,25. We must find the value of the first term in the sequence. In other words, the length of the first piece. So, we know the third term in the sequence is 10. So we can write that T sub 3 equals 10. And we can use this formula. The value of the nth term is AR to the n minus 1. And rewrite this equation entirely in terms of A and R. So AR to the n minus 1 is AR squared, and this must equal 10. And we're going to call this equation 1. Then we also know T sub 6, it's 1,25. So then once again using this formula, AR to the 6 minus 1, so AR to the 5 is 1,25. We can call this equation 2. We're going to solve these two equations simultaneously, so we're going to take equation 2 and divide it by equation 1. So AR to the 5 divided by AR squared must equal 1,25 divided by 10. The a's cancel here, and r to the 5 divided by r squared, of course, is r cubed. And then 1,25 divided by 10 is 0,125. Now we can take the cube root on the right hand side. So r will equal the cube root of 0,125. And we can do this on a calculator. So it's going to be the cube root of 0.125. And this is 0.5 or a half. So r is 0.5. Now remember that we needed to find the value of the first term, or the length of the first piece of string. So now we can use this value of r to find a with. So we can substitute r equal 0.5 or equal to 0.5 into equation 1. So equation 1 is AR squared is 10. So that means that A times 0.5 squared must equal 10. So A will be 10 divided by 0.5 squared. So 10 divided by 0.5 squared. And this comes to 40. So the length of the first piece of string will be 40 centimeters. So this is 40 centimeters. Then in 2.2 it says, find the length of the first 10 pieces of string. So this is relatively simple because all we do is we use a sum formula. So S sub n equals A into R to the n minus 1 all over R minus 1. In other words, we're adding the first 10 lengths. So then we need S sub 10. So it's A, and A we worked out to be 40. So 40 into R, which is 0.5, to the 10 minus 1, all over 0.5 minus 1. So we can do this on a calculator. And we see that this comes to 79.92. So 79.92 centimeters. Let's look at your answer to this question. It says, if each bacterium in a culture divides into 2 bacteria every minute, how many bacteria will be present after 1 hour if there are 4 bacteria at the start? We can start by drawing a picture, and we're going to start by looking at what happens to 1 bacterium. So let's say we start with 1 bacterium. Then after 1 minute, we'll have 2. Each of these 2 will now split up into 2 further bacteria. So then after 2 minutes, we'll have 4. So 4 bacteria, and so forth. So at the beginning, we have 1 bacterium. Then after 1 minute, we'll have 2 bacteria. And after 2 minutes, we will have 4 bacteria. But of course, we are not starting with 1 bacterium. We are starting with 4. So we have 4 to start with. Then after 1 minute, we won't have 2 bacteria. We'll have 8. In other words, 2 times 4. And after 3 minutes, we'll have 4 times 4, which is 16 bacteria. So we see that we have a GP. So it's a GP, and the first term is 4, the second term 8, the third term 16, and so forth. So A, the first term here, of course, is 4. Then R, the common ratio, will be 8 divided by 4, which is 2. Now the question says, how many bacteria will be present after 1 hour? 1 hour represents 60 minutes, so n is equal to 60. And we have to find T sub n. So using the sum formula, we plug in, we want T sub 60. Which is equal to A times R, which is 2, to the n minus 1. So 60 minus 1, which is 59. So let's see what that comes to. 4 times 2 to the power of 59. And this gives 2,3 or 2,31 times 10 to the 18. So 2,31 times 10 to the 18. Some people may be tempted to use a sum formula here, but note that we don't add all the bacteria, because the first one splits into 2 and no longer exists after 1 minute. Then after 2 minutes, these 2 will no longer exist because they would have split into these 4. So we don't use a sum formula, we use the formula for the nth term in this question. In the second question it says, a debt of R157.50 is paid off in annual installments. The installments of each year being half of the previous year's installment. If 80 Rand is paid in the first year, determine how many years the full amount would be paid. So, in how many years we would have paid off this amount. So, we're starting off by paying 80 Rand. That's in the first year. Then in the second year, we pay half of 80 Rand, which is 40. Then 20, etc. Now, all these amounts added up must give 157.5. So we have a geometric series where 80 plus 40 plus 20, etc. must add up to the debt, which is 157.5. We're obviously assuming there's no interest. Now, in this geometric series, we have the first term, A, which is 80. We have the common ratio R, which is 40 divided by 80, which is 0.5 or a half. These must all add to 157.5. So we have the sum to n terms. And we must find the number of years or the number of terms or payments. So we must find n. So we can use a sum formula, S sub n. We substitute n. A is 80. R is 0.5. And this must come to 157.5. Now, we need to solve for n in this equation. 0.5 minus 1 is minus a half. 80 divided by minus a half is minus 160. We can divide the negative 160 into the right-hand side. We can take negative 1 also to the right-hand side. Now we can take the log on both sides. And we can put the n in front of the log using log rules. And now we divide by the log of 0.5, or we divide the log of 0.5 into the right-hand side. And we can find this on a calculator. And we see that n comes to 6. So it will take 6 years to pay off the debt in this way, where we first pay 80 Rand, then in the second year 40 Rand, etc. In number 3 it says, an athlete runs 20 kilometers on a certain Monday. Thereafter, he increases the distance by 10% every day. Calculate the number of kilometers he ran on the following Saturday. So it starts off by running 20 kilometers. This is increased by 10%. So it's 20 times 1,1. Then this is increased by 10%. So this is the Monday, the Tuesday. Then on the Wednesday, you'll run 20 times 1,1 squared, and so forth. Now, from Monday to Saturday is 6 days. So we know that n is equal to 6. A, of course, is 20. R, the common ratio, is 1,1. And as we said, n is equal to 6. Now, we need to find the number of kilometers he ran on the Saturday. This is given by the 6th term in this progression. So we're going to use T sub n equals AR to the n minus 1. We need T sub 6, so it's equal to 20, which is A, times R, to the 6 minus 1, so to the 5. And we can find this on a calculator. So 20 times 1,1 to the 5. So it's 32,21 kilometers. Then in B it says, calculate the number of kilometers he ran altogether over the 6 days. So we basically have to add all these terms up to 6 terms. And we're going to use a sum formula. So we want the sum to 6 terms. So A is 20. R is 1,1. So 1,1 to the 6 minus 1 over 1,1 minus 1. So let's see what this comes to on a calculator. And it's 154,31. So 154,31 kilometers. So let's look at the answer to the first question. The first rectangle has length 21 centimeters, and the next one will be 85% of 21. So 21 times 0.85. So that's a second rectangle going from the bottom up. Then the third one will be 85% of this value. So 21 times 0.85 squared, and so forth. So the first rectangle, the second one, the third one, etc. So we have a GP where the first term A is 21. The common ratio R is 0.85 or 0.85. we must find the length of the 10th rectangle. So n is 10, and we are looking for the 10th term in this sequence. So we're looking for t sub 10. So we can use the formula for t sub 10, or rather t sub n. It's ar to the n minus 1. So t sub 10 will be a, which is 21, times r, which is 0.85, to the n minus 1, so 10 minus 1, which is 9. So let's see what that comes to. So it's going to be 21 times 0.85 to the 9. And this comes to 4,86. So 4,86 centimeters. In the second question it says, calculate the percentage of paper that is colored gray. Now, in order to do this, we need to find the total area of all the colored in rectangles. And for that we need the number of rectangles that are colored in that can fit into the paper. Since each rectangle is 1 centimeter and the distance between colored in rectangles is 1 centimeter as well, we can figure out that the number of rectangles then that are colored in will be 30 divided by 2. In other words, 15. Then secondly, in question 1, we wrote down the lengths of successive rectangles. Now, area equals length times width. And we know that the width of each rectangle is 1 centimeter. So the areas of the rectangles will be the same as their widths, because area will be width times 1 in each case. So then we need to sum all the areas of the colored in rectangles. So let's do that. The area, or the total area of gray rectangles will equal summing these. So it will equal 21 plus 21 times 0.85 plus 21 times 0.85 squared, etc. So we have a geometric series in this case, with the first term a being 21 and r is still 0.85. We figured out that there are 15 gray rectangles, so n is 15, and we need S sub n. So S sub 15. So using the sum formula, S sub 15 is A into R to the n, and n is 15, minus 1, R to the n minus 1, all over R minus 1. So let's see what this comes to. So 21 into 0.85 to the 15 minus 1 divided by 0.85 minus 1. And this is 127,77. And this is the sum of the areas of all the rectangles. In other words, 15 rectangles. So it's centimeters squared. Now we also want to find the area of the sheet of paper, which is 21, in other words, width, times 30, times length. So then the area of the paper is 21 times 30. And this is 630 centimeters squared. So then the percentage colored in will be 127,77 divided by 630 times 100. And it's 20,28%. So 20,28%. So in this question it says, 20 water tanks are decreasing in size in such a way that the volume of each tank is a half the volume of the previous tank. The first tank is empty, but the other 19 tanks are full of water. Would it be possible for the first water tank to hold all the water from the other 19 tanks? Motivate your answer. We can start by letting the volume of the first tank or cylinder be V. So let volume of first cylinder be equal to V. Then the volume of the second cylinder will be a half V, and the third cylinder will be a half of a half V, etc. So we basically have a geometric progression. The first cylinder is V, the next one is a half V, the next one is a half of a half V, in other words a quarter V, the next one will be an eighth V, in other words a half of a quarter V, etc. So these are the volumes of the 20 tanks. Now, the question says, would it be possible for the first water tank to hold all the water from the other 19 tanks? So we basically have to decide whether, when we sum the volumes of the remaining 19 tanks, in other words, when we sum a half V, a quarter V, an eighth V, etc., up to 19 terms, whether that volume will be more or less than the volume of the first tank. So we can set up a series, a half V plus a quarter V plus an eighth V plus up to 19 terms. And we can sum these terms by using the sum formula. So S sub n is A into r to the n minus 1 all over r minus 1. And we want S sub 19. So A, the first term, is a half V. R is a half because we are multiplying by a half each time. So a half to the 19 minus 1 all over a half minus 1. We can simplify this. A half minus 1 is minus a half. So it cancels into the half here and we're left with a negative. So then we have negative V into a half to the 19 minus 1. We can do this on a calculator. So it's a half to the 19 minus 1. that's negative 0.999, etc., multiplied by that negative, or this negative here, will be 0.999, etc., V. Now, 0.999, etc., V is less than 1V. So, 0.999 V is less than V. It's a fraction of V. And this is the volume of the remaining 19 tanks, while this is the volume of the first tank. So we can see that the volume, or the total volume, of the remaining 19 tanks is less than the volume of the first tank. Then, to answer the question, would it be possible for the first tank to hold all the water from the other 19 tanks? And the answer therefore is yes. So we can say that the first tank can hold, and it was, can it hold the water? So the first tank can hold the water from the remaining 19 tanks.